Oh my god. I'm white material.
I can't finish my story.
You can't finish your story. You can't raise your hand either. Is that what's going on? Thank you, Kirk. All the way up. That's a different thing. Okay.
No, I think more people do that.
Like in the South, you mean?
No, I mean.
All right. We are going to be going at a pretty quick pace today. You guys have already seen a lot of kinetics and integrated rate laws. Your workshop this coming week, tomorrow, is going to have you guys working on more practice for integrated rate laws. So today we're going to be trying to apply some of that and talking about trends. How we can use these trends to make predictions, kind of bringing stuff together. So my goal is for you guys today is with real drug data that I'm going to show you guys to determine the rate order of elimination of a drug, and then use that information to decide whether or not a patient should go to the hospital. So let's start the big picture discussion. If you're taking a drug, where is everybody?
I have an exam.
Okay, I guess there's a couple exams right close. Anyone has Sarah's phone number, text her, give her a hard time. Alright, if we take a drug, what does it do? Why do we take, let me see, how do I word this? Why when I take naproxen, can I take one pill every 12 hours? Aleve. You guys know Aleve? Painkiller for joints, old people with rheumatoid arthritis, those kinds of things. So Aleve is every 12 hours. The ibuprofen is every 4 hours. Why? Talk to your neighbor for a second. Why do you take the drugs at such different time intervals? Hey guys. I'm good. Okay, so why is we take some drugs every 4 hours and we take other ones every 8 hours? Salma? Lighter concentration in... Okay, so it's not concentration if it's in a pill, it's the quantity of it, is that what you mean? So if we take a normal pill of ibuprofen, vitamin I, or Advil is the brand name for it. How much ibuprofen is that?
Usually
200 milligrams, okay? So I'm going to call it vitamin I because I take it a little bit too much when I do stupid sports. Okay, what about Aleve? Does anyone know how much is in Aleve? One pill of Aleve. Tell me what. Yes. Old people.
220.
Okay, so good idea, but no. Right? 200 milligrams, 220 milligrams. Is that extra 20 milligrams going to make it last 3 times as long? Okay, so what are some other ideas? Here? True, it's a very different active ingredient. That's why this is not the same as this. So the name brand here is Advil. This one is Aleve. Someone sells it and they're not the company who made it, they have to call it naproxen, otherwise only the company that originally made it can call it Aleve. Right?
Like how long it stays in the blood?
Okay, so how long it stays in the blood? What's another way to say that? Okay, it's half-life, but you gotta be careful there, as we'll talk about later today. Dawn?
You metabolize the naproxen faster.
Okay, so our body doesn't like things that are not supposed to be there. So our body intentionally goes and tries to get rid of everything that's in our blood that's not recognized. And it does that through breaking it down. Metabolism is one way of describing it. Okay, so if we look at time course, here's the concentration of naproxen. Here's time, 0 hours, and here's 12 hours. And here's my vitamin I, concentration and time in hours. Sketch down really briefly what these two graphs look like. Time 0 is where we take the drug, and then 12 hours is all the way to the right. Sketch what the concentration versus time plot looks like for these two drugs. You draw it really little, whatever, just to get it out of your head and put it on a piece of paper. I don't need everyone to have the right answer. I just want you to put down on your paper something that could be a reason why. Think about what it was going to look like, and then try to think about why. That's your Okay, so let's make sure everyone's on the same page. What's the frequency of dosing of Advil? 1 every 4 hours. This is 1 every 6, 8, 12, something like that. I seem to remember on the TV commercials they say like 1 a day kind of thing. So maybe it's 8 hours. What's that? 8 to 12 hours. Okay, so let's say 8 for now. All right. So what is this graph on the left going to look like? Who wants to try to describe it? There?
Well, I was just going to say that I really don't know how this graph is specifically, but I'd say that the peak for the lead is just going to be a little bit higher than the peak for.
Okay, why is the peak on this one going to be a little bit higher?
Because there's more milligrams. And then isn't it like, isn't it being flushed out of your system that is
Okay, so this is about a 10% concentration, maybe, assuming that it goes through from your stomach into your blood this day.
I think this for approximately, no, it would take twice as long to eliminate than Advil would. So this Advil one is super slow. It goes before when the other one goes.
Does someone have something different? So what rate order did I draw these guys in? I drew them in 0 order, and that was just a really blunt tool. And so maybe they're actually first order or second order, or something like that. Okay? And then the graph would be more that shape. But the main thing is, well, then why do you have to take another drug? why do you take it a second time after 8 hours or 12 hours? Don?
Because you're not fixing the problem, you're just numbing it.
So that means that there's some minimum concentration for these that once you drop below a certain concentration is no longer effective. So why don't we just take 3 times as many of these? Then it'll last for 12 hours, right? Why wouldn't we do that? Here?
It'll damage your liver.
So if you take 3 times as much, pops way up. And there's some certain threshold that's called the maximum, what do they call this? It's called the toxic threshold for now.
Is that not LD?
No, it's not lethal. So once you get above a certain concentration, that leads to toxic side effects. That can be liver damage, that can be shut down the nervous system, depends on the drug and different things. So we can't just increase the amount that you take. And this difference between these, that's called the therapeutic window. This is something that drug companies care a lot about. They want smallest possible dose to be effective, so you can give a really small pill. You know, some drugs we take are only 5 milligrams and it's effective. And you want as big of a difference between that and the maximum toxic concentration, or this toxic threshold, that's the minimum toxic concentration. Because you want, people are different sizes, right? If you take 3 ibuprofen and I take 6, it's probably going to be pretty similar because we're the same size. Maybe we have different ways our body interacts with it. But if we have me versus a child taking the same dose, then we're going to be way different concentrations because the same amount of drug is going to be in a very different volume of blood. And remember, concentration is the ratio of solute to solution. So this therapeutic window is really important for drug companies. So what we're going to be talking about now is how to predict how long until we're going to be back within that safe dose after we've taken a overdose by accident. So to do that, let's start looking at a graph here of this drug data. So this is ambroxol. This is the data that we have from I can't remember if this is an average. This is a single female patient that took a 25 milligram dose of ambroxol. And I've given you the data in graphical format on the right. And I've given you concentration versus time in the left 2 columns. And then we've done the manipulations in the next 2 columns that you guys have typically seen in the other representations. So the question here is, let's just start out simple. Let's read the graph. And actually, I need to... So the question is, what is the peak plasma concentration? We're only interested in the drug that's in the blood, so that's why we're looking at the plasma, so the blood. Go ahead and click in your answer to this first question.
You want the time? Here, or the time or concentration?
Hit the blue button if it's not connected to the base.
Yeah.
Toxicity is over that for a long period. Stay over that. That level like that. There's some therapeutic window being between these intervals. All right, couple more seconds. Everybody clicked in? Closing out. Where did you guys get 175 from? Okay, so if we're looking at the graph, is that the most accurate way to get that top data point? How are we going to do that? Let's look at the table. We have a table of data. Let's not ignore data that we have sitting right in front of us, guys. Okay, so the maximum concentration, remember, this left two columns are plotted here on the right for us. So then when we're talking about a drug, there's two phases. You guys already talked about this in binge drinking. What's the first phase of the graph? So that line's going up. What's that called? The absorption phase. Okay? That's how long it takes for a drug to get into our bloodstream, which is where it then has to distribute through the body and have some sort of effect. Now what's the second half of this column? More seconds. Close out. Okay, we have a couple stragglers. But when we're talking about, well, how long does it take to get to a safe level of the drug in our blood? Are we going to consider the absorption phase? We're going to say how long until someone has a safe level of drug in their blood. Are we going to say, well, depends on if they took it and it took an hour to get to where we are. Do you care about how long it took to get to where you are? We care about how long until it gets gone, right? Until we get rid of it. So keep that in mind as we're going through this. All right, so if we're looking back at the graph, I really want you guys, whenever you're analyzing data like this, to think about what's happening in each part of the graph. Specifically that there's a certain amount of time in which it takes to absorb, and then our body goes to work to get rid of it. So I took those three different relationships, time versus concentration, time versus natural log of concentration, and time versus 1 over concentration. I plotted them for you. So I want you guys to, I don't think I gave you space for that. Click in with the rate order of this, the elimination process of hydroxyls. Does that look? You haven't what?
I haven't memorized them yet.
You need to. All right, 10 seconds. Click in your answer. Double check with your neighbor. Okay.
Do you mind putting that projector on?
Sure. So why is almost everyone in agreement that this is a second order elimination process? Hannah.
Because it's a linear graph, like the one with the, I really can't see it.
Okay, so move over. Tell us which one's a linear graph and what that means. What we can infer from that.
Okay, if it's like the one that's half of it, the dividing one, if it's like linear.
Okay, I need you to be more specific. Can someone help her out and be more specific about the wording for this? McKenna?
It's the one over concentration, so.
Careful. It's not 1 over concentration. It's a plot, right? What is it plotting? Okay, so it's a plot, right? It's data. It's an x and a y point. It's saying at what time, and then what's 1 over the concentration. And that relationship is the only one that we see as a linear relationship. And we know from integrated rate laws that that means it must be a second order elimination process. Okay, so in order to use that information, whether it's a differentiated rate law or an integrated rate law, we need to find the rate constant. So what are we going to use in order to find the rate constant? Everybody in? Solid. All right, we're going to use the slope of that graph. If we know the slope of this graph, then we will also know what the rate constant is, which means we can make predictions between concentration and time. So we have our integrated rate law for second order. You guys all know this, right? And so we can start looking at some different stuff here. So click it in. What is the rate constant? You guys want to see the table of data, or you can't read it? If you're not quite sure what you're doing, make sure to raise your hand. Nice using that calculator.
Yeah. Fine. I like the big screen. I don't like when it's like a little screen. More of a visual guy. What?
So that's on the fine. That's on fine. Okay, so if we just put in 2 hours, oh yeah, okay, we have to put concentration for that. But the initial why is not 0? Because 0 is when we're being
If you put 1 over 1 over. Wait. Like the number, if you use the number from the 1 over concentration, and don't put it 1 over.
Divided by the number of hours that have passed. Just from its peak is 1 hour.
Slope of the graph of concentration in the elimination phase. Awesome. All right, let's do another 20 seconds or so. If you are stuck, you need to make sure to raise your hands towards the beginning. How you doing? You nailed it?
I think so. You use different numbers than me.
All right, closing out. You need another 10 seconds to click in your answer? Click in your answer, please. Click in your rate constant. Figure it out. What? How do we find the rate constant? Show me which point you use. Circle.
I use this one, and I use this one
Why that one?
because it actually has a value rather than 0.
All right, everybody, let's come back together. So the big question here is, we need to find the slope of a graph of the 1 over concentration versus time. So what are the data points that we choose? There are a few options. So let me see. Are we going to choose, let me do this. Are we going to choose the 2 points I have in orange?
No.
Why are we not going to use these two, Miata?
Because those points, that's where the drug is being absorbed and not moving.
The 2 points of the orange?
No, the red and blue one.
Okay, great. So the red and the blue one, I think a lot of people initially be like, oh, there's data. I'm going to use data, and I'm going to find the difference between these guys. Did you do that first? Is that what happened?
Well, last
Okay. So if we look at our graph of concentration versus time, what part of this graph are we talking about? We're talking about the elimination phase. That means that you guys have to be looking from this data point on in order for any of these relationships to be of any use whatsoever. Is that fairly reasonable? So then which data points are we going to choose? What's the first data point we could possibly use, Don? So at time 1 hour, when your concentration peaks at 172, but really we're going to be doing the slope of 1 over concentration versus time. So we're going to use 0.0058, and 1 hour is one of our data points. And then what's the other end? What did you guys choose for your second data point you're finding the slope between, Kirk?
I use the 1 for 36 hours
Why?
because it's still part of that linear relationship, but it's really far from our relationship.
So why would it be better to have them further apart?
Because then the slope incorporates the full scope of the data.
Yeah, so then we get, instead of all the variation we have in between, which we get from real data, we have much more of a overall idea of the slope of the graph. Okay? Did anyone use different data points?
I think I just use the one at 2 hours.
Okay, so you can get away with using the one at 2 hours. It might not be exactly the same, but it should be very close. Cosmo?
It's the same thing.
Same thing?
Yeah.
Okay, so let's go take a look at what you guys found. What did you guys click in? What? What is going on?
Is it because I was the only person that got my answer? When I did this, I'm changing, I was like y2 minus y1 over x2 minus x1.
Okay, so let's take a look at this graph. Our data points, so if you notice on this graph, I actually didn't even include 0.5 and 0 time points because 1 over those numbers was really useless. So this data point is the time at 1 hour, and this one out here is at 36 hours. So the slope should be, what is the x value in that top right? And the y? Somewhere around 0.07 something. 7 what? 6.5, I think. I think it was a bit higher. It looks like on that one it was. And then the bottom one, we have 1 hour as our x, and then our y is going to be 0.0058. Okay? So you need to look at the slope of the line as rise over run. That means our change in y over change in x. And so the numbers that I use for that were the y final minus the x final, or sorry, y initial, final minus initial, and then the x the same. All right. If you guys are having trouble with finding the slope, which it seems like a number of us did, then just go back to your simple definition. What is the slope of a graph? Change in y over change in x. 2.0 because we only have 2 sig figs. So that is totally true because, not because of the 0.0058, that's a subtraction, but because this on the bottom is going to be 35 hours. So I agree, it would be 2.0 times 10 to the negative third. Good call, Don. Okay? So that's our K value. Does everyone have that? Everyone has that written down. We're going to use it. So that means that you probably didn't pick the same 2 data points that we did. You might have picked some of the ones in between. So then, so I would use a graphing calculator, whatever you're going to use on the exam. Use that in class because I don't know what happened there, but that shouldn't have happened. All right. So now we have a scenario where this data was collected that we just saw was when an adult was given a 25 milligram dose. One of your friends was stupid and thought that this was actually Tylenol. So they took a 500 milligram dose. Let's hope that there's a really big therapeutic window for this drug, right? So she went and looked up some stuff. She was able to figure out what her blood concentration spiked at. When she realized the mistake, she went online and found that any concentration above 500 nanograms per mil for more than 3 hours can lead to extreme dehydration. You need to get to the hospital for that. So you guys need to figure out whether she needs to go to the hospital or not. And that. All right, so go figure this out. You guys have 3 minutes to figure out if she needs to go to the hospital. You can decide now.
You're looking at the, no,
2 minutes. I can't enter it. You gotta prove it. Don't just select an answer. You gotta prove it.
yeah, you're right,
All right, 1 minute, 15 seconds. All right, 45 seconds.
Why aren't all of you guys raising your hands? So if you were those roles should be over outside of therapeutic that's the CA for outside, right? Then you make this so that's 7,600. 7,000 plus 500. All right. She's going to die because you guys didn't make a decision. All right, so we got to be able to apply these skills that we're working with. So let's see who's going to send her and who's not. All right, so yeah, maybe no, I don't know. Okay, so actually it's even more serious than this, right? So Don, you want to explain what would happen if someone overdosed on this drug? So as far as what the real consequences, she should probably go to the hospital. But what I'm asking about is, can you guys figure out
if she should go to the hospital or not. So how do we even figure this out? How do we use our knowledge of kinetics? How do we apply that to answer a question like this? What relationships are we trying to figure out here?
Well, we need to know how long the ambroxol will stay in her system, because her peak is at 764, but it has to be above 500 for that many hours before it's like a problem. So if it just peaks really quick and then goes down really quick, then she wouldn't have to go to the hospital if it's before the 3 hours. So we would need that for to be able to figure that out.
So let's do another one over here. So if we're to draw this graph, time, what's the important time window here we're looking at? 3 hours, right? That's our do or die. Try to figure out what we're going to do. And then this axis here is what? This is the concentration of the drug. Where's that threshold? Where's this maximum threshold for being safe?
500.
So we have 500 nanograms per mil. And what is she at? So there's different units. So if you guys cannot convert between micro, nano, milli, you need to figure that out before next class. Because we're going to be using these and you guys have to know how to use this. So, Sarah, what is it? What's the constant?
7,640 nanograms.
So that's probably off our charts with the scale, right? 7,641, is it? 40 nanograms per mil. Is she okay? No. Okay? The question is, well, what is the relationship between concentration and time? Do we have some sort of equation that helps us figure out if there's a certain concentration, how long until we get below another concentration? Don?
Isn't the zero order?
Well, so 0, first, and second order all have these types of relationships. What did we say that this is? We said this is second order. You guys already figured that out. So concentration versus time is still completely accurate. It's just not going to be linear. So we max out somewhere up here. So she got this huge initial dose. And then the question is, where does this cross? So how did you guys answer this question? Did anyone, how did you lay out the problem? Did anyone get that far? Val?
I don't know if I got the right answer, but I solved for what the final concentration would be. So I plugged T equal to 3 hours. We want to know what the concentration is at 3 hours. So you plug
And then
in.
what would you solve for?
We would solve for the final concentration. So the initial concentration would be the peak that she reached. This is what we did.
Well, what was the initial concentration?
7,640.
Nanograms.
Yeah. Well, it would, you plug 1 over that number.
So we don't have everything we need, though, to solve for that final time written here. What is the one other thing that we need? Wouldn't it be nice if we had a rate constant? What was that?
Oh yeah, I used that.
So 2.03 times 10 to the negative third. What are the units? I don't remember off the top of my head.
It's ng over ml times hours.
Ng over
ml. It was mg over ml in parentheses times hours.
so you flipped that. I get it. All right. Okay, can we figure out the final concentration at 3 hours? That's something you guys can do. Do it. And as you do it, think about another way you can solve this problem too.
this is minutes or seconds and this is hours. And that you can't do this.
Oh, yeah.
So you have to be really careful. I'm not saying it's not. I'm just saying that without your units, you can't see it.
Right.
You can figure it out. So the y-axis, you guys can go. And you were using
Right.
so the process is right. Just make sure you have everything. Right. So what is the 3? Is that 3 hours total?
That's right. You got one.
Okay, so where's the let's go back here. Where's your initial concentration? And then the question is it above this threshold? Are you trying to say that this time is between here and here?
Well, like, no, I know that's not your way to do it. So we just like estimate it.
Anything we look at, concentration. The question is just what relationship gives us a linear relationship? What relationship is like linear? So, what's your right now? I think you're on the right track. I'm not sure if everything worked out. All right. So then how do we use this information to solve? How do we use that information that we all pulled out of this problem to solve for whether she has to go to the hospital or not? Someone want to talk through it? Sarah?
So we multiplied our constant by, well, we used this second order equation, so we multiplied our constant by the number of hours. And
Let's write out the second order first.
So it's 1 over is the initial concentration or final? 1 over final concentration equals constant times time plus 1 over initial concentration. And then our constant was 2.0 times 10 to the negative third milligrams per milliliter times hours. Multiplied by the 3 hours that she had. Plus 1 over our initial concentration. And we converted it to nanograms from micrograms, which is 7,640.
Okay. And one of the things I want to point out that I talked to some of you about as we walked around, let's make really sure that we're using the same units here. So those hours are really important that we kept our units to make sure that we're talking about hours for a rate constant, hours for the actual number, the amount of time we're looking at. So if you solve for everything that we have there, what did you find?
You get 0.006, and then you have to do 1 divided by that.
So that is 1 over the final concentration.
Yeah.
So we can't just stop there.
And then you get 163.108. So the final concentration is less than 500, so she doesn't need to go to the hospital.
If she survives with her breathing for those 3 hours, she doesn't have to. Did that surprise you guys that it dropped down below the threshold so quickly? Why would that be less surprising? Anyone think about why it came down so fast?
Because it's a second order equation, so the line, it's not going to be linear, it's going to be more sloped.
Because it's what? Huh?
I don't know.
It's an exponential decay. So if you have an overdose of something, you would love for it to be second order, because that means it's an exponential decay. It means it's really, really steep in the beginning, and then it flattens out over time. If it was zero order, you'd be screwed. You're done. Because that means that it would be a constant. I mean, it could be a really steep slope. Could be something we get rid of really quickly. Done?
Because I did everything up to the 0.006 and I got that. Why are you dividing by 1 again?
So remember over here, that whole equation that we just found, 0.006, is equal to 1 over the final concentration. We want to know what is the final concentration, and we found 1 over that. So we can, however you want to rearrange it algebraically. Okay? How else could we have answered this question? Does anyone do this a different way? Nobody? I know Shane did. Justin.
I didn't do it, but I have the, I guess the 500 nanograms. That's the concentration you need to reach before you get to like a safe concentration. So if we plug that in as the final concentration, and then add the initial 7,640, and then the constant, and we can find the amount of time it would take to reach 500 nanograms.
What do you guys think about that? Does that make sense? So on the exam, I will give you guys questions in both directions. I will ask you, maybe you'll have the time, and you'll need to figure out what the concentration reaches at that point. Maybe I'll just give you a question like this, but you'll have to justify it, and you can use either one of these two approaches. But we need to be able to use these integrated rate laws to say that there is a defined relationship of how concentration changes with time. We can use historical data to make future predictions. That's what I want you to be able to do. Mia?
So for that, time would have to be less than 3 hours, right? Or not?
Yep.
Or not really?
So we have to figure out, well, does it get below 500 in less than 3 hours? Shane, what did you find? So we find that if we do it this way, 0.93 hours, because we're on that really steep part of the exponential decay curve. Questions? Can you guys do this on your own? Can you design a dosing label from this? Can you design how frequently this drug should be taken? That's what we're going to be doing next Thursday in class. All right? So that wasn't nearly as fast as I'd hoped. Surprise. In class. All right, so I solved it both ways here. And you guys can check this out afterwards if you're not quite sure on how these different parts came about. Okay? And I'm going to have you guys, here's an extra problem for you to solve. I'll post these right after class. Actually, no, we need to answer this question. How would we answer this question? Talk to your neighbor for a second. How would we answer this question? Don't solve it. I want to know how you would solve it. Talk to people, man. No. You don't need it. No. What are you guys saying? How do we figure this out?
You would, since it's asking for half, 1 over 0.5.
So say again? No, I just didn't.
No, I don't
didn't
think that
follow you.
makes sense.
So what is half the concentration? Where does that go?
I thought that it was like if you have the initial would be 1 and then the final would be 0.5. So that sounds
Well, is the initial 1 here?
of the
What's the initial? All right, let's bring it together, guys.
So how do we set up a way to solve this problem? Someone talk me through the process? Mia?
You would divide 250 in half, since that's what the final concentration has to be.
What is that number then? So it's 125, and what is that number?
That's the final concentration after a certain amount of time that you're trying to find.
And then what's the initial concentration?
250.
So then what are you solving for, and how do you solve for that, Sarah?
You're solving for time, so we're putting it into the second order equation again.
Okay, so what I'm trying to get you guys in the mind state of is half-life. It sounds like a new complex term. Can someone put it in your own words? What is half-life?
How long it takes for, like say you have concentrate like a substance, how long the half-life is, how long it takes for the amount that you originally had to cut in half,
It's not the amount,
or like the concentration.
concentration.
Yeah.
So it's the amount of time to get to half of the initial concentration. That's it. That's how easy this is. It's really easy here. Just, well, we know the initial is 250. When does it get to 125? What's the next half-life? Well, that's when it gets to 62.5. And when it gets to 31.25. Okay? So keep that in mind. Don't be scared by these numbers, all right? So what we're going to be doing is we're going to be talking about using this equation to solve for the half-life. So you guys, we can use this whole relationship that we already have. What did I do to get this equation? I changed it a little bit, right? What about 1 over initial?
You subtracted it from.
Yeah, I subtracted it from the right side, so now they're both on the left side. And so what's that fraction going to look like? 1 over 125 minus 1 over 250. You guys okay with that? So the generic way to write this out is a little t. So t is usually time. That's terrible. But if we want to say, well, what is the half-life? The way that we're going to write it is like this. T 1/2. So we know our rate constant times the half-life is equal to, when the concentration is half of the initial, minus 1 over the initial. Is everyone okay with that? More generic way of writing out what we just did. How did I get that? Kirk? How did I do that last little manipulation there?
1 divided by 1/2 is 2.
Okay, great. 1 divided by 1/2 is 2. So everyone agreed that the 1 over 0.5 is the same as 2 over initial concentration. Okay, then what is 2 over something minus 1 over something? So that's our half-life equation. So if we have this equation equals kT 1/2, we want to know what the half-life is. So we can just rearrange it. So T 1/2, we can divide both sides by K, 1 over the initial concentration times K. Is the half-life going to be different if we look at different concentrations? Why? Because if we change this number, that number is going to be different. Okay, everyone okay with that? For second order, this is the generic equation for half-life. If you know it's second order, now you have one more equation that lets you talk about how concentration changes with time. If I know the initial concentration, and I know rate constant, I can tell you what the half-life is going to be from that starting concentration. But that means that halfway through the reaction, it means it's going to be a different half-life. And then when it's later on, that half-life is going to be even different as well. So if we did it for this exact problem, the half-life is about 1.97 hours for the student, because we're down on the flatter part of that exponential curve. Let's see how you answer this, see if we're on the same page.
could be because I maybe used all the digits from previously, so not 0.00203. I might have had more digits that I plugged in. All right, everyone clicked in? All right, who wants to justify their answer? Thomas?
You have two concentrations, one that's 200. The time that it's going to take to get to 50 and 100, so they're two half-lives.
So what we're trying to get at is the half-life for any second order reaction. The bigger the concentration is, what happens to half-life? The bigger the denominator is, does that make the value larger or smaller? Smaller. So it's an inverse relationship. The higher the concentration is, the quicker the half-life is. The smaller the concentration is, the longer the half-life is. Which is false? B. Yeah. So if the denominator gets bigger, which is a higher concentration, what happens to that fraction? So look at the equation and you answer that for yourself. All right, so for this next part, we're going to be talking about half-life. So predict the time at which half the original concentration is reached, and we're going to have us derive the half-life equations for 0, first, and second order. All right, let's do this. This is a graph of concentration versus time. We're going to be looking at concentration versus time for 0, first, and second order, and we're going to start making some inferences about half-life. So take about 30 seconds to go ahead and read this problem. Use that graph if you want. That's for a first order reaction. Do about 10 more, 15 more seconds. So Demetrius, what are your thoughts? How does the half-life of a first-order reaction change as the concentration of a reactant changes? Where do you see that on the graph?
The red line.
Circle.
Is it like this part?
Why is it that? Because it says half-life?
I mean, yeah.
Yeah. Okay, fair enough, fair enough. I gave you a graph that says that on it. What's the initial concentration of this reaction? 0.20. What's half of that? 0.10. How much time did that take? 7 seconds. All right. What's half of 0.10? So to go from... How much time was that? Another 7 seconds. So 7 seconds, 14. To go to half of that again is now another, so we're at 21 seconds, right? Can you guys start to visually see where half-lives are? We go down to half the concentration and we see how long it took for that change in concentration to occur. So the cool thing is that for any first-order reaction, we don't need to know the concentration to know the half-life. So a lot of times in medical field, they'll say what's the half-life of that drug. And you can tell the person to go screw themselves if they're talking about anything other than first order. Because otherwise it totally depends on the initial concentration, so we cannot generically say. Is that fair? We'll see zero order again in a second here. And though the way that we can describe that, I think, I thought everyone was on the same page on that one. I guess not. Go back. So where were you guys getting different things, increases and decreases from? Were you not reading the graph the way that we talked through it? Any questions on it?
I guess I know I did, but I was thinking about. No, I think I did the same. But I think I was getting confused because it like the half-life was like the concentration was decreasing.
Yeah, so we're not looking at the slope of this curve right now. We're just looking at where it starts and then how long it takes to get to half of that concentration. And then now we're at 0.10 here. How long does it take to get to half of that concentration? Megan, comment?
So half-life refers to like the amount of time.
It's the amount of time it takes to get from the concentration we're at to half of that concentration.
It's not measure of concentration.
Correct. It depends on concentration for second order, but it doesn't depend on concentration for first order. So let's talk about these half-lives for first order. So really in this graph, I'm just trying to show you that if this is a first order decay, we can look at it and we can say, well, it looks like the amount of time it takes to get to half of the concentration each time is the same. So let me spin it another way. If we look at a graph and we identify that the half-life is the same no matter what our concentration is, what can we say about the rate order? We can turn around and say it's first order. So these are all tools to interconvert. We're not saying that this is a different set of rules. This is just looking deeper within the trends we've already seen. All right, so I want you guys to rewrite this equation and do what we did a minute ago, but plug in T1/2 for time, and then write the appropriate amount for initial and final concentration. Show how those are related to each other at half-life. Take about 1 minute to write this out. Rewrite that equation for T1/2 equals, and then show how initial and final concentration are related to each other. Half-life of approximately that's first order. No. No. Please make an effort to write out T1/2 equals as a way to rearrange that equation. So write out T1/2 equals, and then do that whole equation, and then show how A and T How does the concentration compare? Where are you going? What is half? Define half out here. We started with a certain amount. When we half that, that's what half-life is. It's the amount of time it took to bring it in and out of half the initial concentration. So then, how does this keep up? Sure? Which one's the issue? Okay, so are we going to be increasing or decreasing concentration? The reactant's going away. This one's smaller. Okay, so what is the key here? What is the key connection that's going to help us simplify an equation like this for the one point in time when we reach half the initial concentration? Anyone help me out? So the question is, how are we going to write a simplified version of that equation? Mia?
First you have to plug in the half of the initial concentration for the final concentration.
Perfect. That's exactly what we need to do. So the concentration at our time t that's half-life, that is 1/2 of the initial concentration. We just defined that, right? Half-life is when we've reached half of the initial concentration. What questions do you guys have on that? That's really the crux of this problem. So then we just take that and we substitute this in here. And then we rearrange to simplify for t. So if we do that, we can use a couple different forms of this equation. This is one using the rule of logs. So if you're not comfortable with how I did this, I could really briefly show that we have ln of concentration of A at time t minus ln of concentration of A at time 0 equals minus kt. Are you guys okay with that? And then if we want to change the sign over here, we multiply both sides by -1. Okay with that? Multiplied everything on the left by -1, and then I flip the 2 just so it's one minus the other. And then rule of logs says that if you have ln of one thing minus ln of another, you do ln of the one divided by the other. Okay? Rule of logs, if you're not comfortable with using logarithms, you need to now, because now in the rest of the semester we're going to be using logs all the time. So figure out how to use them, what the rules are for rearranging and re-expressing. If this looked confusing to you, please go find a YouTube video that teaches you how to use logs. Or talk to your math teachers, because you guys are all in math class, right? You guys already passed those, right? So that means you know how to use them. Great. All right. Okay. So with this relationship here, what do I put in the top or the bottom? Do I change either one of these? Thomas?
The final has to be 1/2 of the initial.
So I'm going to do the bottom of this is going to be half of the initial. Okay? So if I do that, then I have the bottom is 0.5 times the initial. And the really nice thing about arranging the equation this way is that we have a really, really simple relationship. So what is the half-life equation then for first order? And this is only for first order. Are you guys noticing this different for different orders now? Second order does change with concentration. Does this change with concentration? Nope. So McKenna, what do you have for the final half-life equation for first order? Okay, so T1/2 equals, what do I do here to isolate T1/2? Divide both sides by k. So T1/2 equals natural log of 1 over 0.5 times k. Or if I have 0.5 on the bottom, I can just do 2 on top, right? Anytime we realize that we have a first order reaction, now we have another equation that can tell us about how this concentration changes with time. What questions do you guys have?
When we're doing this on a calculator, we just type in the ln of n2 every time.
ln of 2 divided by the rate constant is the half-life. So all different reactions have different rate constants. So what is one type of reaction that is always first order? Radioactive decay. So if we have carbon-14 versus a cobalt derivative versus a beryllium derivative, if they're all radioactive decay, the only thing that's different is that rate constant. And what about zero order? If we find that a reaction is zero order, or we see a graph like this, both of which are fine, how does the half-life change as the concentration of our reactant goes down? And can I get an honest showing of hands? How many people read about half-life before class today? Do you guys feel like we're pulling teeth? I feel like we're pulling teeth.
We talked about it a little bit in biology.
Okay. So I have suggested readings for class specifically because I want you guys to come in, not having never heard of a term before, and I feel like today we spent about half an hour more working through this stuff than we should have. I really need you guys to step up your game so we don't waste class time. We didn't even get to work any problems, right? We just talked about the really basics of this, and I feel like that was a huge waste of our time today. So if you guys want to get something out of this class, we're at like, I don't know, half an hour behind is a lot of time in this part of the semester. So please do everyone in this class a favor and read at least a little bit, at least get some of the terms down and come with questions about how these things fit together. I would really appreciate that, and I think your classmates would too. So if we look at this, what are you guys finding? Okay. So if we're looking at half-life to get from the initial concentration down to half of that, at first took about, what, 30 seconds? A little bit over 30 seconds? To get to the second half-life, that was only about 10 seconds. And it got smaller and smaller and smaller after that. So you guys should be able to look at any graph of concentration versus time, and just by eyeballing what the half-lives are, if half-life doesn't change the whole way down, what rate order is that going to be? It's always going to be first order. And then we can say, well, oh, if it's swooping, well, and it's not the same half-life, we know it's second order. Or if the half-life, if it's a straight line, we know it's zero order. There's a lot of different ways we can apply this information. And so if we do the exact same thing we just did, but for zero order this time, where we rearrange our integrated rate law, and you guys can work through this afterwards if you want to convince yourself of how this all fits together. But our half-life equation now is the initial concentration divided by 2K. So if you guys know our rate constant, whatever our initial concentration is, the bigger the concentration, the bigger the half-life. Let's see if you guys have been awake. Closing out. Got it, Sabrina? So as our concentration goes down, our half-life gets bigger. Okay? And so we can rearrange the equation as we did here, same way we did in the very beginning, right? We have our three half-life equations now that add to all the other equations we have. So what is the half-life of dinitrogen pentoxide? You know what? In the last 2 minutes of class, I think I'm going to leave this up to you guys. There's half-life questions in the homework. You guys are going to have to work on those yourself. You can come to office hours tomorrow. But I feel like the last thing I wanted to introduce in class was not about this. So I think I'm going to let you guys go back through these. And the last thing that I want to pull up is about the energetics of reactions. So you guys have seen these diagrams before, right? So let's spend the last minute in class making sure that we're all on the same page as far as what these diagrams represent. Dr. Neighbor, if you're not quite sure. Yeah, Kurt?
Is that E one of the choices, or is that vertical?
So that vertical axis is E for energy.
I just want to make sure.
Sorry about that. So it's A, B, or C. Talking about where on that energy graph is the initial energy of the initial reactants. Everyone clicked in? Okay. What is that peak then? What is this energy at the top here? It's not the activation energy. That peak is, that's the transition state. That's how much energy is at the least stable point in the reaction. What part of this graph is activation energy?
Is it the change
This is how much energy needs to go into break some bonds in the first place. And then how much energy is released overall by the reaction. Which one shows that? That's the change in reaction overall. So you guys have a little bit of this on your homework this weekend. We're going to start bringing this up again on Tuesday. If you guys get into the homework, dig into it early. If you have trouble working with your integrated rate laws, you can come to office hours tomorrow or let me know. We can find some time to meet. Thanks, guys.